Okay, so I just also wanted to announce there will be a final makeup class this Friday. There was one that we hadn't made up from earlier in the semester. We are roughly on schedule, but I thought that it would be nice to have that class so that the last lecture can be mostly a recap of what we have done rather than cramming new material into it. So I will announce that as well, same time on Friday in this room. Okay. So what we will do today and Friday's class is chapter 9 of the book, which is going to be on distributed system security. I usually do this more briefly than other material because security is a topic on its own. There is actually an entire course that you can take, grad level course on security. So rather than duplicating the same content, this is going to be a high level overview number one today, and then next time we'll talk a little bit about applications. We will look at payment systems and e-commerce systems and see how these ideas, the basic concepts that we will talk about today and to some extent next time, are actually used in real world applications, and that's really where I think some of the material is more relevant to this class. What I'm going to do today is simply introduce distributed system security, talk a little bit about cryptography. If you have time, we'll start talking about authentication. Okay, so let me start with some basic background. Okay, so some of this may be familiar to you, so please bear with me just so that we are all have the same background. So this is a picture that depicts why we need security in distributed systems. So in the distributed systems, you have nodes that are communicating with one another. Communication may go over arbitrary networks, including the internet or any communication network. Right? And we cannot make any assumptions on what is happening on the network with respect to who can listen on to the communication. So the assumption is if A and B are communicating, these are nodes. Okay, in computer rather security terminology, you personify them and call them Alice and Bob, which we will also use here. So Alice and Bob are talking to one another over a network. Any intruder can listen to any packets that are going back and forth. Okay? So that's our assumption, or what's referred to as a threat model. Okay, the intruder may eavesdrop, which means simply listen to packets that are going by. Okay? The intruder can remove packets, meaning just delete them and never reaches the other end. It can modify the packet. It can insert new messages. Okay, all of this is possible. Okay, you can read, record, and then replay messages, meaning you can take all the messages that are being sent by Alice, in this case to Bob, and at a later time play them back as if Alice is sending them again. That's also possible. Okay? That's called a replay attack. And so you can intercept, interrupt, modify, fabricate. So all of these things are possible. And the question we really want to ask is, what are some basic mechanisms you can use from a security standpoint to prevent this from happening? Okay? So there are 4 different topics that are typically common in security sort of literature. The first one is encryption and cryptography. So this is going to ensure what is called secrecy. It's going to prevent an eavesdropper that is intercepting messages from understanding what's the content of the message because you have encrypted. Okay, so we're going to do encryption is the first topic. The second topic is called authentication. This is to prove to the other party you are who you claim to be. So if Alice is sending a message to Bob saying, I'm Alice and here is the message, how is Bob to know that it actually came from Alice? So to do this, you have to authenticate, which is somehow prove to Bob that you are indeed Alice and not someone else masquerading as Alice. Okay, that's the problem of authentication. Okay. Authorization is a problem which we will not really talk about much when we talk about firewalls. Next time we'll talk a little bit about this. So this is to verify that you have the rights to perform this action. Okay. Maybe you encrypted your message, maybe you're authenticated that you are indeed Alice, but then the system needs to check that if Alice is performing an operation, and in this case Bob is a computing system, not a person, that Alice has the rights to do whatever they are requesting. Okay, so that is the problem of authorization. And auditing is also important. Again, something we will not talk about here, but it's becoming an important field. Embarrassing. So auditing problem is basically the problem of going back after something has happened and trying to understand what happened. So if an intruder broke into a system, okay, first thing is you're going to stop this problem. But once you have stopped it, okay, you have to understand what was the reason the intruder could get in to begin with. Okay, what were the holes in the system that allowed the intruder to come in? This is often done through auditing. And then there is an entire field called forensics, security forensics, which allow you to go back, analyze, understand, saying what should you have done that can prevent this from happening in the future. Okay, what caused the problem to begin with? So all of these problems come under auditing. So much of our discussion is going to focus on the first two topics, but we keep in mind that there are these other facets of security that are just as important. Okay. So with that, let's start talking about the first problem. We'll talk about encryption and cryptography. Okay. So here is a simple example where Alice is a person, Bob is a computer. Alice is simply trying to log on to the machine. Okay. Usually this is done by supplying a username and password, okay, to log on to a machine. Okay, in this case, the intruder can listen to all the packets that are going back and forth. Okay. Now, if you use a protocol such as Telnet or FTP, okay, these are either protocols to log into a system or log in and then upload or download files. All of the packets that are going from the user to the application are actually unencrypted. So when Telnet or FTP prompts you saying enter your username, you type your username, that's going in plain text. The packet actually has your username in text. So if you look at the contents of your network packet, you will see the username in there. And when it prompts you for the password is also going in plain text. Okay, so if you actually intruder eavesdrops on this message and gets hold of this message, your password and username will be revealed because it's not encrypted. Okay? So clearly doing this the old way, okay, is not the right way to do it if you want to have better security. Okay? Now all modern protocols such as SSH and SFTP will not do this. These are old style protocols, but there are some rudimentary systems that still support them, okay, in some shape or form. These may not be real computers, but some network devices and things like that, they may still support rudimentary versions of these protocols where you do not have any encryption. Okay. So basically what we want to do is somehow prevent this from happening. Okay. And I should also mention that many network resources are often unprotected. If you're actually logging on to a server machine, you probably use robust protocols, SSH and so on. But if you're using a router, okay, and trying to change the configuration of a router, often they don't have the right level of security built in. Okay, they may not be using encrypted protocols. In fact, routers can receive routing updates without even checking where it came from. You receive a routing update, you trust that the other router is the one that sent you that routing update. So you can easily send spoofed packets where you have a fake sending address and send an update, and that may cause the router to get misconfigured. Okay? So the problem is we are neither using encryption nor using authentication, and if these devices don't check what is going on, bad things can happen. Okay? So you can really take down, intruder can take down a system, or actually in this case your network, without any problems. Okay? And you have seen this happening from email and spam already, right? So you can see that you can send an email to anyone and just change the sender address. Okay, the mail system often may not even check where it came from. You get a mail that is presumably from your friend, but then is offering you money to go to Nigeria or some such thing, right? So that you clearly know that that's not a true message, but this can be done because the protocol is inherently not secure. And so with that, we'll talk about encryption. Okay, this is just basics. We'll keep building on this. So what does encryption do? Encryption takes any message that you are going to send and transforms it in some way so that if an intruder can see this transformed message, they cannot derive the contents of the original message. Right? So you basically, so essentially you have what is called the plain text, which is the original unencrypted message, and then you apply an encryption algorithm. Okay, this is often done using a key that you supply to the algorithm. So that encryption algorithm is going to take a plain text, is going to take this key, and it's going to construct a new text which is called a ciphertext, which is the encrypted form of the message. Right? This encrypted message is what is going to be sent over a network. Okay? And the assumption is if the algorithm is robust, okay, to security attacks, just looking at the ciphertext does not allow the intruder to figure out what was the original text. Okay, for that you need to know the key, which is secret, and you need to know the encryption algorithm. The encryption algorithm is often known. Okay, they're all public, but the key is the part that's secret. So you shouldn't be able to guess the key, or you should be able to derive the original message. Okay, so the intruder can still intercept ciphertext transmission, can intercept plain and ciphertext pairs, which we will see can lead to certain forms of attacks, and obtain the decryption algorithm, okay, which may be known depending on what yours, but you shouldn't be able to derive the original. Okay. Any algorithm that supports those three properties is a good one. I will talk about a few. Okay, here is the simplest form of encryption algorithm. It's simply called a substitution cipher. Okay. That's the letters of the alphabet. Okay. You simply construct a cipher which is anytime there's A in the message, you're going to replace it with P. So it's a random permutation of the original. Okay. So for every letter, you have an alternate letter. You permuted the alphabet, essentially. So all you're doing is, if this is your plain text, you're going to look at this substitution cipher, and for every letter you're going to look at its substitute, and that's what you're going to have. Okay. So this is the ciphertext that you will send in this case. Okay. And the assumption is the receiver also has this mapping available to it, so that you can do the reverse and get the original back. Okay. Very simple form of encryption was used 2000 years ago by armies sending encrypted messages. Okay. Not anymore, doesn't work. Okay, here are the reasons why it doesn't work. So first of all, you have to realize, so this is called symmetric key, because you have to use the same key at the sender and the receiver to encrypt or decrypt. Okay. Now you have 26 factorial possible keys. Those are all the permutations that are available to you. Okay. One of them is going to be the real one. Okay. Now, although the intruder doesn't know which is the one that has been used, you can subject this algorithm to other forms of statistical attacks and derive the cipher. Okay. For instance, if you know that E is the most common letter in the English alphabet, the is the most common word, you can simply subject the ciphertext to analysis, saying what's the most common letter occurring here. Okay? Because if E is the most common letter here, some substitute letter will be the most common one, and you will realize that that is the substitute for E. So you make some guesses like this. Now then it becomes like a crossword puzzle where you know some parts of the word. So you can look at the dictionary and say what are possible words that map here. And you figure out the word, you find out some more substitution. And soon you derive the key without knowing the key. Okay? So this form of attacks are basically possible. Not only possible, they can be easily done. Okay, and then you can figure out. This is not even a brute force attack. Okay? A brute force attack would basically say, I'm going to enumerate all 26 factorial keys. I'm going to try each of them in turn. And if the ciphertext turns out to be something that doesn't look like gibberish, then I assume that's my key. Okay, so you can do that as well. That's called a brute force attack. But you can do something more sophisticated than that and get the key. Okay. Now we'll talk about some real algorithm. That was just a trivial one. So this one is called DES, Data Encryption Standard. It was an encryption algorithm that was proposed by the US government some number of years ago. It is no longer secure because it is more vulnerable to brute force attack these days. Okay, but it is nevertheless worth looking at, because the more complex ones are hard to explain, and this is not a course on security or anything like that. So I just thought we'll do the simple one. Okay. So the way DES works is it takes your arbitrary message, chops it up into 64-bit chunks. Okay. The encryption and decryption algorithm is published. Everyone knows it, including the sender, receiver, as well as the intruder. Okay. Now, what is not known is the key. Okay. So it should not be possible to guess the key. And the way the key works is you take a 64, or rather a 56-bit key. Okay. That's a bit string. You pick a key. Okay. And you subject the original algorithm to 19 stages of transformation, as I will show on the next slide. During each stage, you take a subset, you create a new key from the original key, encrypt, then you scramble, then you pick another key from the original key, encrypt, scramble, and so on. So you're essentially encrypting the original text 16 times, and then you get the final ciphertext. So here is basically, I'll show some pictures. So this is essentially the encryption. Okay. So you'll take a 64-bit string, Okay, the message is chopped up into 64-bit strings. So you take the left 32-bit and the left, this is the left and the right. So you take the left and the right, and this is your encryption function. So you take a key, okay, you have from the original key, you're going to derive 16 keys using that algorithm. It will tell you pick this substring and that other substring, and that gives you a key. So you'll take the key, you'll take the right half of the message, and you'll apply the encryption function, which is also published in DES. I'm not going to show the function, but it takes the key and it scrambles the message and it gives you a new 32-bit message. And that, or rather, you take that and you XOR it with the left part. Okay? That gives you the new right part, and then the right part is simply put in the left part. And you repeat this recursively 16 times. Okay, so there's a picture here that's going to show you how this works. So you take a 56-bit key, okay, you have 28 bits, 28-bit strings. You're going to essentially do this, do a rotate left extract. So this is how you're going to extract the keys, the smaller keys for each stage. Okay, and then within the stages themselves, you do round 1, then you get the next key, you do the same thing for round 2, you get the next version of the key, do the same thing for round 3, and so on. So this is your final encrypted algorithm. Okay? Because it is symmetric, you can do that in reverse and get back your original. Okay? Now it's not important to understand the details of DES and so on. What is actually more relevant is that the algorithm is no longer secure because 56-bit keys are not long enough for today's computational resources that I have available to you for brute force attacks. Okay? Typically, the shorter the key, the more feasible it is to enumerate all possible keys and try it and see what makes sense. Okay? As computers become faster, you can take clusters of computers and try to use brute force attacks. And 56 bits is just not enough. So a replacement that was suggested for DES was DES3, which used basically 3 56-bit strings. Okay? That's 168 bits. Okay? Even that is no longer as secure. So the most modern ones that you use today are AES encryption. These use 256 bits, 512 bits, or 1024 bits. The larger the key, or the longer the key, the more computationally expensive is the encryption. Okay, the encryption becomes more computationally expensive because the key is bigger, but also the brute force attacks are harder to launch because enumerating 2 to the power 1024 keys is a much bigger problem than enumerating 2 to the power 56 different keys. Okay? Huge numbers of orders of magnitude difference. So you cannot launch brute force attacks. So simply the encryption algorithms are using longer and longer keys, which prevent brute force attacks. Okay? 10 years from now, maybe AES will not be enough because the computers 10 years from now will be much faster or more parallelism built in. Okay? So it's always a race as to who can stay ahead. Okay? The hackers always try to use some clever brute force attacks, and then the people who design the standard say we make it more robust by using longer keys or just using a different encryption algorithm altogether. Yeah, that's the part really you need to keep in mind as to choosing the key, choosing the algorithm. All of these are important aspects of choosing a good encryption algorithm for your application. Now, regardless of how secure your encryption is, there is this whole other problem of picking a key and sharing that key between the sender and the receiver. That is just as important. Okay? If you do not have a secure way to generate a key or share the key, your encryption algorithm is going to be useless. Okay? Because an intruder can get the key, they don't need to do anything in order to decrypt the message. So you need to have, just as you pick a secure algorithm, picking that key that you're going to use and sharing it with the recipient is important. So the analogy to think of is maybe you have a big lock for your house. Okay? But if you take the key for the house and put it under the mat because you're too lazy to carry it with you, the lock is essentially useless if the intruder can get your key. Okay? Same is true here. If you do not guard your encryption key and the hacker can actually hack into a machine and get the key, all the encryption algorithm becomes pointless. Okay? So the problem of key distribution is just as important as the problem of picking a good encryption algorithm. There are many ways to do it. We will see several. Okay, one way to do this is to use a trusted third party. Okay, in this case, you basically, Alice and Bob want to communicate. They want to They agree on what encryption algorithm to use, and they want to generate a key for this encryption, for this session. Okay? One way to do this is both of them go to a trusted agent and say, generate a key for us. The trusted agent securely sends the key to Alice and Bob, and that's important. Okay, you have to send it securely, otherwise the key is going to be known to the intruder. The intruder can listen on to those messages. But once you securely have the key, you can send messages back and forth. Remember that it is, if Alice decides to unilaterally generate a key, that's also possible without a trusted third party. But then Alice needs a secure mechanism to first send the key to Bob and then send the encryption algorithm. Because just sending the encrypted messages without sending the key is not going to work for Bob. Bob needs the key to decrypt. So there will be protocols we will see that do not use trusted third parties. They simply, the sender generates the key, but there's a way to send it to the recipient securely. Okay, so now those were what are referred to as symmetric key encryption algorithms. Now we will see asymmetric algorithms, and most common example of this is what is referred to as public key cryptography, which you probably have either heard of, or if you use SSH and SSH keys, you probably used it already. Okay, so what happens in this case is rather than using the same key for the sender and receiver, you have two keys. Okay? There's what's called a private key and a public key. Okay? The public key is the key that you give to anyone who wants to decrypt your messages. The private key you keep to yourself. Okay? Now, if you want to send a message to someone, okay, you encrypt it with your private key. And then you give the public key, and the public key you anyway make public. It doesn't matter who knows it. Okay? And then the person at the other end can decrypt your message using the public key. Okay? Or rather, it's the other way around. If somebody wants to send you a message, they take your public key, okay? They encrypt the message and they send it to you. And since your private key is only known to you, only you can decrypt that message and no one else. Okay? So basically, the receiver makes known its encryption key, which is referred to as the public key. The receiver keeps the decryption or the private key secret. To send a message, you get that person. To send a message to someone, you get their public key, which is known. Okay? You take your text and you encrypt it with the public key. But the message can only be decrypted by the intended recipient because it's assumed that the private key is secret. Okay? So, and then the reason it works is the encryption algorithm is such that if you take a message, you apply the encryption key, and then you take that message and you apply the decryption key, you'll get back the original message. Okay, so there are two keys here. We'll call them K1 and K2. Okay, there could be public or private key. Take any message M and you apply the encryption algorithm, and then you take the other key and you apply it, you'll get back M. That's the property of the encryption algorithm. You can do this the other way as well. You can take M and apply K1. So it is. Okay, so there are two keys here. Okay, in symmetric key, the same thing was true, except that there was one key which basically said you do this, and then you use the same key and you do this, that gives you M. Okay, you apply the same key on the encrypted text, you get back the original text. Okay, so now we'll talk a little bit about, so this is basically how it works. So you have a text, you take and you are sending a message to Bob, you are going to take the public key, encrypt it, send the ciphertext, it's visible. Okay, only the private key is known here, so you will be able to decrypt it. Okay. Now the question is, what are some good algorithms? The most common one here is what is called RSA, which you probably have heard of as well. We'll talk a little bit about how it works. Yeah, so it's a very widely used algorithm for public key cryptography. Algorithm basically depends on the difficulty of factoring very large integers. So if you give a very large integer, several hundred digits long, and say go find the prime factors of this integer, that is a computationally difficult problem. There aren't any efficient algorithms known to do that. Okay, so the whole algorithm depends on this one property saying given very large integers, finding their prime factors is going to be hard. Okay, and that's how you are going to decide your encryption and decryption key. And this is basically the basics of RSA. So to find your, so first you got to generate a public and private key, and this is the technique to do that. Okay, so you're given two prime numbers. So first you have to pick two prime numbers P and Q that are reasonably large. Okay, in this case they're greater than 10 to the power 100. So two very large prime numbers. Okay. And then you compute the product of those two primes. N is P times Q, and then you also compute another term Z, which is P minus 1 times Q minus 1. Okay, so you compute two integers that are the product of those two primes and the product of the prime minus 1. Okay. And then you have to choose D, another integer D, which has no common factors with Z, which basically means E times D is 1 mod Z. Okay, so these are, so D and Z should be relatively prime. They shouldn't have any factors in common. Okay, so you pick that D. Okay, in this case, so what happens is now you have three numbers. So you have the encryption key, which is that value there, and N, which you picked here. Okay. And the D is actually the secret, that is your private key. E and N are basically your public key. That's the part that's made public. Okay, and I'll show you how this works in just a moment. We'll run through an example to do this. Okay, now we'll also see why it works. So this is just how you pick the key. Okay, then we'll talk a little bit about how it works and we'll do some examples. So now what happens is if you have a message to encrypt, you're again going to chop it up into fixed size bit strings, and then this is how you're going to encrypt. So you take a string, you do the string to the power E mod N. Okay? That's the encryption. The decryption is you take the encrypted string and you do that power D. Okay, that's your private key, and that should give you back the original, and we'll again see why that is the case. Okay? So now to break RSA, you will have to basically be able to, given N, be able to do factorize. If you have to factorize N and get the original P and Q. That is what we said is the hard problem, which is why this is a good encryption algorithm. Because factoring 200-digit numbers takes a very long time, even on today's computers. Okay, so let's do some examples very quick. So we'll say, so first we have to pick two prime numbers, P and Q. Okay, let's say there are 3 and 11, both are prime. Okay, so N is 33, product of the two. Okay. P minus 1 times Q minus 1 is 20. Okay, 2 times 10. Okay. So now you have to find some number that has no prime factors with 20. Okay, so we pick D is 7. 7 and 20 have no prime factors in common. Okay. Clear, right? Okay, so now you have to compute E such that this is true. E times D is P minus 1 times Q minus 1 plus 1. Put K is 1. So this is 20. Okay. So this sign becomes 21. D is 7. Okay. So you enter. So E becomes 3. Okay. So encryption key is 3. Okay. And N is 33. D. So this is your decryption key, 7. So now if you take this and simply do what we said here, take any arbitrary bit string and do that to the power E mod N, that will give you the encryption key. And then you take that and do that to the power D, you will actually get back the integer. You can just try this if you want on any arbitrary bit string, meaning the bit string is going to be an integer. You take any integer, take E, N and D, and you will be able to actually see that happening. So you'll see how the encryption and decryption works. Now we'll ask the question, why does this even work? Why is it that if you do this and then you take that to the power D, you get back the original string? Okay, that is a property from, that's a math property from number theory. Okay, this is the outline of how it works. Okay, so the crucial number theory result that RSA depends on is if P and Q are prime, not B to the power P minus 1 times Q minus 1 mod PQ is 1. Okay. That's a known number theory result. Okay. So let's just take that as a given. Okay. That's some property that comes from math. So now what we will do is, essentially you are given an integer B. Okay. You basically do B to the power E. Okay. And then if you do that to the power D, and there's a mod N here which are ignored, that should get you back B. That's our basic hypothesis using that number theory result. So let's do B to the power E to the power D, which is B to the power ED. Okay. And so now what you do is ED is actually going the way you picked it. If you remember, the way you picked it was this. Okay, so we are going to simply take the right expression and substitute it here. So b to the power et is b to the power this for some k. Okay? So then basically you take that plus 1 and you take b out, and now you get b to the power p minus 1 q minus 1, and so on k times. Okay? But now, as we said, this result, you put that result there, that mod pq is 1, the mod is not shown there. So each of these terms becomes 1. So this becomes b times 1 times 1 times 1, which gives you value. Okay, so it's simple. Once you given that number theory property, simple arithmetic to prove to yourself that b to the power e to the power d is actually going to get you. This is b to the power ed, okay, and this is going to get you back d because ed is essentially this property. Okay, that's just a rough sketch of what is behind RSA. Don't have to go into too many details of why that number theory result is true. Let's just take that as a given. Any questions on this? Okay, so now let's talk about some interesting stuff as to what might be some problems with RSA if not done right. So here are some things you can do. So B is public key, well known. The public keys are made public. That's why they're called public. Okay. So now what you can do is you can take for every possible string or every possible value of bi, you can compute b to the power e. That's how you encrypt. Right? So you basically, let's say, you take 2-bit strings. Okay? So the 4 possible strings, original strings are 0, 1, 0, 0, 1, 0, 0, 1, and 1, 1. Okay? So now what you will do is you will maintain a table where you will take this is b. You will do b to the power e. Okay, so you will take 0, 0 to the power e, you will do 0, 1 to the power e, and so on. Okay? And you will keep this table with you. Now, as these messages are going by with this the encrypted version, you are going to actually look, saying here is the encrypted version. What in my table does it match? Okay, so if you see x, y, and then you have constructed this table, you say the original is 0, 1. So I say, okay, what you are sending is 0, 1 because the encrypted version I just saw that go by is x, y. Okay, is that clear what I'm saying? Okay, so now basically what we have is a table of pre-computed original strings and the original string encrypted with the public key. Okay, now every time I see this go by, I just look at the table. Okay, because I enumerated all possible strings and all possible encrypted versions of those strings. So I look at the table and I look at the original. I get the original back. So even though I do not have the private key, you are able to decrypt in this case. Okay, so now does that mean that there is something wrong with RSA? No, that's not the problem. This is not an issue with RSA, it's the issue of what you actually did here. Okay, so what is the problem or what do we do to address this problem?
The intruder is just enumerating. Okay, so he has plain text, ciphertext, pairs.
Yeah.
And if that set is limited, then you can essentially.
Yeah. So basically we said you take the original message, you chop it up into strings, fixed size strings, and then you encrypt the fixed size string. Now if you do this in a naive way where that fixed size string is very small, then you can enumerate all possible strings of that fixed size and actually have plain text ciphertext pairs. Here you chose 2-bit strings. This is very silly to do because there are only 4 possible strings. So any message you are going to chop it up into 2-bit strings and encrypt it. So there are only 4 values. So the intruder made the job very easy for the intruder to guess because you can keep this table of 4 entries. Okay? So the moral is this string has to be large enough that it cannot be enumerated by any human. So if you pick 32-bit strings, you have 2 to the power 32 possible values to enumerate. If you took 64-bit string, that's 2 to the power 64. So pick it large enough so that this table can never be computed using a brute force attack. Okay, 2-bit string clearly doesn't work. Okay, nothing. So it has to be really large in some sense. So that is the moral is this is not a problem of RSA. This is how you're implementing the algorithm. Is you have to choose BI big enough so that you cannot launch this brute force attack. Okay, so that's one. So even if you pick the key properly, this is an implementation problem where you actually did not pick BI large enough, made it easy for an intruder to launch a brute force attack, okay, on a well-known algorithm that's not used very well. Okay. Here is another problem which you may have heard of, the hard bleed attack, rather, which is a problem that is actually man in the middle. It's called man in the middle attack. Okay. Here is how it basically works. Okay. This is a trivial man in the middle attack. Alice wants to communicate with Bob. Okay. First problem for Alice to communicate with Bob is to get Bob's private key, or rather public key. Okay. How should Alice get it? Okay, let's say Alice simply sends a message to Bob saying, give me your public key. Okay, here's the intruder sitting in between. Intruder actually intercepts the message, in this case, and simply forwards the original message back to Bob saying, give me your key. Okay. Bob sends the actual public key. Okay. Intruder intercepts the message, keeps that public key, and then sends its public key to Alice. Okay. So now Alice has gotten a different public key from the one asked, because that message was intercepted. The public key was swapped out with a different one. Okay. So now what Alice is going to do is Alice is going to take this different public key, encrypt a message, and send it off, assuming that only Bob knows the private key. So this message is harmless to anyone else. But in reality, it has been encrypted with the intruder's public key, not Bob's public key, because you swapped the key out. So now for the intruder, it's trivial to take their actual private key, decrypt the message, get its contents, re-encrypt it with the real public key, and just send it to Bob. Okay. So Bob now gets the message and decrypts it, and it looks like it has come from Alice. So transparently, an intruder is sitting in the middle, decrypting every message, re-encrypting it correctly, and sending it. So neither Alice nor Bob know that this is happening, because everything is transparent. It only happened because you actually gave the wrong private public key without someone realizing. Okay. So you have, again, this is referred to as a man in the middle attack, where an intruder is sitting in the middle and basically doing something that is causing problems. Okay. And it's transparent. You don't even know this is happening because you just got the wrong key. So this is another problem you have to avoid. And this problem again has nothing to do with RSA. This problem is because the key distribution was broken. You are not able to get the key in a secure way. You let somebody else send a different key to you pretending to be Bob in this case. Okay. So this is what I said. Key distribution is just as important as the encryption algorithm. You get a bad key, or you get a key that impersonates someone else, you are going to actually be vulnerable to these forms of attacks. Okay. So this is the kind of problems that led to all the heartbleed problems that you've been hearing about. Essentially a man in the middle attack. Much more sophisticated than this, but this is the essential idea of what kinds of problems can go on. Any questions on this? Okay, so I am going to do the authentication part of the lecture next. So that was all about encryption. So we talked about symmetric key cryptography and public key cryptography. Symmetric key encryption basically uses a single key between the sender and the receiver. Public key cryptography uses two keys, a public key and a private key. The private key should only be known to you. Public key is what you give to someone. Okay? SSH and all of these protocols actually use public key cryptography. You generate a key, and then you give the public key to the machine and you authenticate with your private key. Okay, this is how SSH will work, and this is how many other protocols will work that we'll look at. HTTPS is also based on some version of public key cryptography. All that is coming after we talk about authentication. Okay. So now we'll talk. Now we'll talk about the problem of authentication. Encryption, we know. Encryption is going to ensure secrecy. Authentication is the problem of proving to someone that you are who you claim to be. Okay, so if somebody asks you for your password, you shouldn't give it, because you know most of the time that's a bogus request. But how do you know? Sometimes somebody may call you from the phone and say, I'm such and such, I need this information. You trust that they take them for their word. How do you make them prove to you? That's really the problem of authentication. Okay, so how does a receiver know a remote communication entity is who they claim to be? Okay, then I will look at some very trivial protocols that will have some obvious problems. Then we'll come up with some that are going to be based on this notion of cryptography to do authentication. So first of all, if you just get a plain text message saying I am Alice, you can't trust the message because anyone can send that message. Truly, an intruder could have sent you a message saying I'm Alice. You can't believe that just because somebody is telling you they are some person X. Okay, so that's your trivial protocol that we will ignore. Okay. Now let's assume these are Alice and Bob are machines. You could check saying I'm going to actually check the IP address of the machine this message came from, and I will authenticate based on IP addresses, okay, rather than the username. This was username authentication, that's IP address authentication. Now that also doesn't work because it is relatively straightforward to do what is called IP spoofing, which is generate an IP packet but change the sender address. Okay, so you can insert whatever sender address you want and inject it into the network. The receiver will receive it and it will look at the source field. It will look like some other machine and the machine it came from. Okay, this is very easy to do. There are libraries you can get that allow you to inject a packet with a different source address. Okay, so somewhat trivial to do. So you can't just look at network packets and authenticate based on IP addresses alone. Neither can you use username. Okay, the thing that is most common is basically to issue a challenge saying if you say you're Alice, prove to me that you're Alice. That's how you do authentication. Simplest form of issuing a challenge is to say, tell me your password. If you're Alice, you know a secret password to prove to me that you are Alice, and assuming that only Alice knows her password, she can supply it and you can authenticate. And in this case, the assumption is the challenge, the response to the challenge is something that only the correct person can generate. In this case, the password is only known to Alice, so Alice can tell you the password. As I said earlier, if the password is sent unencrypted, then intruder can actually snoop on it, get the password. Next time around, the intruder can impersonate the original person and supply this password. Okay? So you need to ensure that when you have this protocol exchange, all the messages are encrypted so that your secret is not revealed to someone else. So the simplest thing to do in this case is to encrypt all of the messages that we just showed here. So this is our authentication protocol version 3.1, where Alice sends a message to Bob saying, I am Alice. It's encrypted. Okay. Bob will decrypt the message which says, I am Alice. Okay. Now in this case, if the encryption key is the secret that's only known to Alice and Bob, then you're done. You don't need to ask for a password because the very fact that this encryption key is only known to Alice and Bob is reason enough that only Alice could have sent that encrypted message. Okay, is that clear? What we just said. So this is one scenario. Now this one doesn't quite work because it is vulnerable to what is called a replay attack. Okay. Intruder can just simply intercept this encrypted form of the packet, keep it, okay, and then at some later point resend that encrypted packet. Okay, now because it's still encrypted, you haven't done anything to the packet, the machine will assume that it came from the right party. Okay. So this is going to be vulnerable to what are referred to as playback or replay attacks, where you can simply record a set of packets and resend it from a different person or different entity can resend it and now you get into your system. It doesn't work. So the way typically is the right way to do authentication is to not use a single password, but to use one-time passwords. So one-time passwords are passwords that will never be reused. So even if an encrypted version of the password is stored somewhere, it cannot be replayed at a later point in time. Okay? This is the most common way to actually do encryption. Is one-time passwords are called nonces, or one-time challenges, and we'll see how to do this. So it is once in a life. So in this case, it will simply be an integer. Okay, that is generated once in a lifetime. Okay, and this is basically the way it is going to be used. Okay. Alice is going to send a message to Bob saying, I'm Alice, okay, unencrypted. Okay. Bob will say, fine, okay, here is a challenge. Here is a once in a lifetime integer that I'm going to send you. And now you encrypt it and resend it back to you. Okay. So then basically you send this nonce. Okay? Alice is going to encrypt the nonce with the secret key that's only known to Alice and Bob. And now you send the encrypted version of the key. You don't send the password, you send the encrypted version of the challenge. Okay? Bob is going to decrypt that message and say, okay, what has come back is an encrypted version of the nonce I just sent, so you're authenticated. This is not vulnerable to replay attack because next time Alice is going to use this, will generate a different nonce. This nonce will never be repeated in the lifetime of this application. Okay, it's like using a one-time password, which is never going to be reused. So if the password is never reused, the intruder cannot store a list of encrypted password because this nonce will never be repeated, so you'll never actually get to use this and replay it. Okay, so simply resending this encrypted password doesn't help because next time the nonce will be different. So when you decrypt it, you will not get the challenge that was issued to you. So these are also called challenge response protocols. Okay, so you issue one-time challenges to authenticate. Is that clear? Okay, so now there's the issue here saying what's the problem with nonce? It really has to be once in a lifetime value. Okay, so the integer has to be chosen from 0 to n so that it's never repeated, and it has to be large enough taking into account the lifetime of the application. Okay, because real integers are fixed bits, 32, 64. If you overflow and you reset, okay, you're going to be repeating the same integer. So you need to pick it large enough so this never happens. You need to worry about the lifetime of that application. Okay, whatever it is, 5 years, 10 years, 25 years. Okay. Now you can also do this using authentication using public key cryptography. This is also very common. So this is how it is going to work. You are going to send a message saying I'm Alice. Bob is going to send once in a lifetime nonce. Saying here is a challenge. You prove to me you are Alice. Alice is going to take her private key, only known to Alice, encrypt that nonce, send it back. Bob knows Alice's public key. Public keys are well known. Right? So you'll take the public key, you'll decrypt the message that has come. If the nonce is what comes back, then you say, okay, this must be Alice. Okay, so if you have somebody's public key, you can issue this challenge, have them respond, and then you verify that it was indeed Alice. So this is authentication using public key cryptography. Any questions on this? Okay, so now here are some issues that you have to take into account. So this is the man in the middle attack, which is going to cause the same problem that I was talking about earlier. The problem with this approach is to ensure that the public key is actually the right one that is known to you. Right, so here is basically what might happen. Let's say the intruder is called Trudy. Trudy sends a message to Bob saying, I'm Alice, impersonating Alice. Okay, Bob is going to actually try to send a message to Alice saying, here is a nonce which Trudy will intercept. Trudy will send a message to Bob with the encrypted key. Okay? And then Bob is at this point, Bob has to get the public key in order to decrypt it. This is where the protocol will go wrong. In order to decrypt this nonce, okay, Bob has to actually get to know the Alice's public key. So he'll send a message saying, send me the public key so I can verify. Trudy will intercept this message and actually send the wrong key in this case. Okay, so which will allow Bob to authenticate. So what this again proves is the same problem that occurred last time is protocol is only secure if the public keys are distributed in a secure way. Right? Simply putting your public key on your web page, lots of people put their PGP keys on their web page, is not necessarily secure because when you retrieve HTTP is not secure. If you receive over HTTP, somebody can swap it out. Okay? Or somebody can hack into the machine and change your key momentarily. Okay? So these are all insecure ways. They are widely used, but they are not necessarily secure ways because just because you got it from the person's web page doesn't mean it's the real key because the message could have been intercepted in transit. The HTTP is encrypted. So you have all of these problems that can actually occur when you do authentication. Okay, most of this stem from not the problem with the underlying encryption protocol, the problem with key distribution. Okay, so that is where a lot of these protocols go wrong even though the protocols themselves are secure. questions here? Public. Okay, so this is the man in the middle attack. I already showed it. I'm going to skip that. Okay. So now, with having done the basics of encryption and basics of authentication, let us look at some more interesting problems. The first one that we'll look at is what is called digital signatures. So basically, the goal of a digital signature is to electronically sign a document, okay, just as you physically sign a document. So it should have two properties. First property is that you should be able to sign it and the other person should be able to verify that you signed it. Okay. And the second property is if the person comes back to you and says you signed this document, okay, you shouldn't be able to say no, I did not sign it. Meaning that here is your signature, you should have signed. So those are the two properties. So basically, the sender cannot repudiate, which means claim later that I never signed it. If your signature is on a check, you cannot say that I did not sign it because that is your signature. It matches your origin. And the other property is somebody shouldn't be able to forge your signature. So you should be able to send a fake message saying here is the signature. Okay. Now this public key cryptography can be used to sign any document. Okay. So you can sign an email, you can sign electronic documents, and then that basically the other person can verify you signed it. And also once they have the signed version of the document, they can prove to you that only you could have signed it. Okay, so both of those properties are true. The simplest way to do this is to use again public key cryptography. So if you want to send a signed message to let's say a party, you simply take your private key, you encrypt that document with your private key and send it. That is as good as your signature. Only you know the private key. Right? Now the other person, how do they verify that you signed it? They know your public key, so they can use the public key and decrypt it. If you get the original document, it shows you signed it, because only you could have encrypted it. Right? And you cannot claim that you did not sign it because the encrypted document only you could have generated, because it's encrypted with your private key, only you have it. Okay? So this very trivial way to have a digital signature is to simply encrypt any document or any message, okay, with your private key. That is like putting your signature on that document. The encrypted form of the document is your signed version of your document. Okay. Now, so you cannot deny it, you sent it, the other person can verify it and so on. But this is not really how digital signatures are actually used. And the reason for this is very computationally expensive. Your public and private keys are very long keys. This document could be of arbitrary length. It could be a 100-page Word document. You sit and encrypt a 100-page Word document, it's going to take a long time to do. Okay, so you want to get the same property of a digital signature, but in a more efficient way. This is just a very rudimentary way to do a digital signature. Okay, so we will talk about this thing called a message digest, and then we'll come back to how you can use this message digest to generate digital signatures. Okay. So encrypting and decrypting entire messages is expensive. So what we will do is, rather than signing the entire document, we will compute a smaller hash of that document. We'll take that document, we'll apply a hash function, and we'll get a smaller hash. And we'll actually sign the hash, not the original document itself. Okay. So here you have a hash function that converts a variable length string to a fixed length hash. Variable length string is your document. It could be of arbitrary size. Think of it as a long string. Okay. You apply the hash, it will give you a fixed size hash string. Okay. Then what you will do is you will actually sign the hash of M, not M itself. M is the original message. So you will basically take the hash and you will encrypt the hash with the public key or your private key. And then you send the document and the signature. This is the signature. Okay, that's the original document. Okay, then you send the two. Okay, now in this case, you can, if M gets altered in transit, you can claim you never signed it, because M prime will have a different hash. Okay, what you signed is this hash. Okay, so if somebody shows up with a different altered document and say you signed it, you can prove that no, I never signed it, because M prime gives hash of M prime. And when I decrypt this, I get a different hash. So the hashes don't match. So I never signed it off. So you can claim that you never signed something you did not actually sign. Okay? And the person can also verify that you actually signed M because they can compute the hash, they can decrypt this hash using a public key and compare the two. Since the hashes will match in this case, they will be assured that you signed the document. So both of those properties will hold in this case. Okay? Now it's important that the hash function be chosen carefully. Because if it's not chosen carefully, if two documents map onto the same hash, then the person can actually prove that some other string was signed, not the string that you actually signed. So in other words, the hash function should be such that given a digest or a hash X, it should be infeasible to find a string that maps onto it. Right? Because this is like saying, I know you signed this hash of M. Let me compute all documents that map onto it and now claim that you signed all of them. That shouldn't be possible. Okay? And it basically, the other thing is the probability of a collision should be very, very small. It can't be zero by definition of a hash function. Hash functions will have collisions. The probability of a collision should be very small so that you shouldn't have two documents that will map onto the same hash. If you find a hashing function that has those properties, then you can actually have a more computationally efficient digital signature, not the original one. You compute a smaller hash, you sign the hash much cheaper. Hashing is cheaper than encryption. Okay, and signing a smaller string is cheaper than signing a bigger string. So this is how you'll actually do digital signatures. Okay. There are many hashing functions. I'm not going to go into the details of them. Here is one called MD5, okay, which is message digest 5. It uses 512 mixed strings. So it takes any arbitrary message and converts that into a smaller message. Now, this is also no longer very secure. It is vulnerable to these forms of attacks because the key that is used to do the hashing is small enough that you can launch brute force attacks. That's a given a digest. Can I start enumerating different strings and construct something that will give me the hash? Okay, so as a result, this is not used anymore. What is actually used are hash functions called SHA hash functions, secure hash algorithms. Okay? They use much larger bits than MD5. They use either 160 bits SHA-2. There's SHA-2, which uses 256 or 512 bits, which makes it much harder for collisions to happen or to guess a string given a hash, such that the string maps onto the hash. Okay? So these hashing functions are what are actually used. If you use any encryption library that has hashing function, most likely it will be SHA. It will have MD5, which is an older version of a hash function, but it is no longer secure in the sense that you can actually launch brute force attacks on it. Okay, so that is message digest. So let's talk a little bit now about the whole problem of having a trusted server to distribute keys. So this key distribution, as I said, is an important problem. And there are many ways to handle it. One is to go to a trusted agent, and then you ask the trusted agent to give you a key. The key is generated by the trusted agent. Okay, so here is this trusted agent is often referred to as a key distribution center or a KDC. So here is how it works. So basically, each entity has a key that only the KDC and they know in advance. Okay, this could be done when the machine is set up or some such thing. Okay. So if Alice wants to talk to Bob, what Alice is going to do is send a message to the KDC saying, I am Alice, I want to send a message to Bob, generate a key for us. Okay. So the KDC is going to generate a session key, which is called K, the key for A and B, Alice and Bob, to talk to one another. That key itself is encrypted with a key that only Alice and the KDC know. That's the pre-configured key. So only Alice can decrypt this message and get the session key out. Okay. The same key is also sent to Bob, but encrypted using the key that only Bob and the KDC know. Okay. So now you have generated a key, you have distributed it securely to Alice and Bob using the keys that only they know and the KDC knows. So this gives now a key for Alice and Bob to communicate with one another, which basically is generated for you by the KDC. And this requires a trusted third party, in this case the KDC, and also this requires a key for each entity and the KDC to communicate securely. That key has to be pre-configured. Otherwise, you have the same recursive problem. You can't say who's going to give me this key, how do I get that security? So that has to be done by, let's say, when you configure the machine or some such thing. Same protocol here where the key is actually sent by Alice to Bob, not the KDC. In this case, Alice says, I want to talk to Bob, give me a key, and suddenly the KDC sends a key to Bob. Bob never doesn't even know who is Alice, why does she want to talk to me, or any such thing, and the key shows up. If you don't want that to happen, then Alice can actually get the same protocol. You can make a small modification, okay, and let Alice send that key to Bob. In this case, what is going to happen is we're going to send the same message to the KDC. KDC will actually give you the session key, okay, that is encrypted with your key. It's going to also send you the other key that you're supposed to send to Bob. Okay, so that's the one that is encrypted by Bob's, the key that is symmetric key between Bob and the KDC. And then Alice will send a message saying, I am Alice, here is our session key. Okay, the session key is only decrypted by Bob. Okay, this is how you can generate a key and securely send it to the other party. Okay. That's basic as idea here is keys, session keys also have to be sent in an encrypted form. Okay, so this is the bootstrapping before the actual communication begins. Okay, and if that is not done securely, in all of the previous cases, the public keys were sent unencrypted. This is why they were vulnerable to man-in-the-middle attacks. Here we are trying to get away from that, and the key distribution itself relies on some form of encryption. In this case, it also relies on a trusted third party to be in between. Any questions on this? Okay, so there is a more sophisticated version of this protocol that I will not talk about. It uses the same property as before, which is called a Needham-Schroeder protocol. Needham-Schroeder protocol does two things. It generates a key and it also does authentication. So it uses this once-in-a-lifetime nonce so that you cannot reuse the session key again. Okay, so key is tied to a session. The session has a once-in-a-lifetime nonce so that if the key comes back to you again, you will not be able to reuse it after the session ends. Okay, so you achieve this once-in-a-lifetime session key by injecting a nonce and verifying the nonce in addition to giving the original key itself. Okay, so essentially what Alice will do is she'll generate a nonce. Alice, I'm Alice, I want to talk to Bob, send it to the KDC. KDC will generate a session key. It will give you the key that you're supposed to send to Bob. Okay? And then when Alice sends that to Bob, Bob will actually reply with another challenge saying, prove to me that you are Alice, not some other intruder. And then Alice can then basically reply by taking the session key and re-encrypting the nonce and sending it back, which proves that this is a key that is only valid for this session. It's only sent by Alice and so on. So it achieves multiple purposes. Okay, there's a little more message exchange than the previous one, which is very straightforward. But the only real thing that's happening is the messages include a once-in-a-lifetime nonce in it, so that the key is tied to a specific session, cannot be reused, cannot be vulnerable to replay attacks. Okay. Popular protocol called Needham-Schroeder protocol used in many different scenarios. So now we'll talk about not using an intermediate. So all of those session key exchanges required you to have a key distribution center. What if you want to send an encrypted message to your friend, you don't have a key distribution center? If there's no trusted third party, what would you do? So in this case, what you can do is you can, of course, use public key cryptography. You will send a message saying, I'm Alice, here is a nonce, and you will take Bob's public key and encrypt the message and send it. Bob's public key is known to Alice. Okay, so the terminology in the book is slightly different from what I was using. This essentially means it's a public key and it's Bob's public key. Okay. So now Bob gets a message and a once-in-a-lifetime nonce. So then Bob can decrypt the message with this. This can be extracted using Bob's private key. So then Bob is going to reply with that nonce. Okay. It's going to generate a new nonce and then also generate a once-in-a-lifetime session key here. Okay. So the session key is generated by Bob, and all three things are then encrypted with Alice's public key, which is known to Bob. So when Alice gets this back, she can verify that this message came in the response to the original message, because the original nonce is in the message. there's a new nonce that you have to reply back, and there's a session key. So what Alice will do is she'll extract these three contents, take this nonce, this key, and then re-encrypt it and send it. So when Bob gets it back, Bob had generated this symmetric key, so Bob knows the key. Bob can extract the nonce and verify that it is the same nonce that was sent to Alice. Okay. So here you have done mutual authentication. Okay. You also generated a session key. So you're authenticating so that Alice and Bob know that they're talking to the people who they claim to be. You also generated a session key for use, okay, which is going to be the key that is used for all subsequent messages. Okay, the important thing here is subsequent messages will not use public keys and private keys because they're longer and more expensive. So what you did was you used the public key cryptography to bootstrap the protocol, and you generated a smaller session key, which is more efficient to use for subsequent messages. Because you did not have to do this, you could have simply continued to use the other person's public key to send them messages, and you basically get back messages that are encrypted with your public key. The assumption is your public keys are long enough that they are expensive. So you use the keys just to bootstrap the communication, to do the authentication and generate a symmetric key that is then going to be used for subsequent messages. Okay, is that clear? What is going on here? This does not need a KDC. Okay. It still doesn't get away from the problem of you need to know the other person's public key securely. That problem has not gone away. Okay, we'll see how to address that problem as well. But assuming you know the public keys, you can bootstrap. Okay, so now we can ask the question, how do you get somebody's public key securely to begin with? Okay, so here is one way to do it. You basically go to a trusted server rather than some other entity, okay, and say, you send a message. So first of all, we'll assume that you know the trusted server's public key. Otherwise, you can't do it. So if you know the trusted server's public key, you send a encrypted message saying, give me Bob's key. You send it encrypted with the trusted server. So no intruder can decrypt this message and figure out whose key you are asking for. Because you have signed it can only be decrypted with the trusted server's private key. So getting this message is practically useless for any other intruder. So now the trusted server decrypts it, and then what the trusted server does is you basically put Bob's public key encrypted with Alice's public key, and the trusted server has a database of all public keys, say, and then you send that back. So now you have gone to a trusted server and securely retrieved someone's public key. And so this will not be vulnerable to any attacks because both these messages are encrypted, and the private keys are only known to the corresponding party, so you can't figure out what is going on. Okay. So this is one way to figure out how to get somebody's public key. Okay. You go to a trusted third party. It requires you to go and ask for the public key. Okay. I'll also mention another way to do this, which is basically this notion of certificates. Okay, so you probably have heard of a digital certificate. Digital certificate is a similar scenario, but you don't actually go and talk to the trusted third party in advance. What the trusted third party does is it gives you a public key, okay, and it is signed by that trusted third party. Okay, so it's a certificate, it's a certified public key. So think of it as a public key that is encrypted with the trusted third party's key. Okay. So now you can basically go to Bob and say, give me your public key. Rather than getting an unencrypted public key, you get the public key in the form of a certificate. Okay. And then what you can do, since you know the trusted server's public key is known to everyone and is decrypted with that key, you can first of all extract it. And second of all, you can verify that the trusted party is telling you that that is the right key because it is certified by the trusted party. Okay. So this is basically how actually the verification works. When you connect to a server, let's say a web server, you don't actually go to a trusted third party and actively retrieve the public key of the server. You simply ask the server, the server gives you a pre-signed message from the, so the key is actually signed by the trusted third party saying, here is my key, it's signed by an entity that we all trust, so you can verify that this is my key. Okay? So the certificate will say something like this, and the certificate will be, you take the private key of the trusted third party and will say, this is server cnn.com and this is the public key. Okay, that's the certificate. Okay, so now you know the public key of the trusted third party that's assumed to be well known. So you can extract it and see that, okay, this is actually the public key and this is the machine for which it is supposed to be used, and that's the machine I'm connected to. Okay. It's the same protocol, but without actually sending message to get the verification, you send a pre-signed message to do exactly the same verification. Okay. This is how most browsers work. When you in a web browser, you have a list of the trusted third parties are called certification authorities. Okay, so if you actually go into your browser's preference or settings pane and you click on the security thing, it will show you a list of trusted third parties that your browser actually trusts. Will have companies like VeriSign and all of these companies that are in the business of issuing certificates. Okay? So your browser is preloaded with the public key of most of these trusted third parties. So if some entity comes along, some web server comes along and says, here's a certificate issued by a trusted third party that you already trust. It has actually signed my key. You can verify that it's my key. The browser can easily verify. Okay, that's actually what happens. Then you take the public key that's already encoded in your browser, you decrypt that certificate, you verify that it is actually the name on the certificate is right and the key is what it is, and then you use that key to communicate. Okay, so the right way to actually distribute keys securely is either have everyone go to a trusted third parties and retrieve it dynamically, or have the trusted third party give you signed keys. Okay, so there's a signature of the trusted third party on the key, so you can verify that the key hasn't been changed and it belongs to whoever it is, because the server's name or the person's name is in the certificate. Okay. So if you actually, if you go and if you have an HTTPS session and you click on that green icon, it will show you the certificate. You will see who has signed it, what it looks like, and so on. All of that is actually encoded in the certificate. Okay, so that is how all of these techniques work. Okay, typically, when you use public key cryptography for communication. Okay, so I'm going to skip this Diffie-Hellman today, and so we've run out of time. So next time we'll talk a little bit about access control, firewalls. Basically, we'll switch to application. So we have done all the basics. We talked about encryption, we talked about authentication, we talked about signing messages, and we talked about how to do secure key distribution. Okay. So with all of those, now we can look at how firewalls work, how secure email works, how digital money works, digital payments work. So that is what we will do next time. Okay, just applications of this secure protocol. So we'll stop here today.